Welcome back. So the first method we're going to discuss is multidimensional scaling. Multidimensional scaling is one of the dimension reduction techniques that we discuss in this course. And as I outlined in the previous video, multidimensional scaling focuses on preserving the distances. I will not talk too much in detail. I will really primarily show you two examples. The first is a slightly silly example, but it really helps for the intuition behind the method. So we can think of a map, a geographical map with cities on it, with capitals on it, as a 2D representation, a two-dimensional representation of information, where every city has a certain X and Y coordinate. This is the location of the city. Now, in this case, this is kind of the target. Like, imagine we would calculate the distances between each of those cities and make a table. And you could get a table like here on the left. You get a table where every number represents the distance between a pair of points. From Istanbul to London is 1,500 kilometers. From Paris to London is 200 kilometers, etc. And we can then use MDS. Normally we would not do this, but it's only as a demonstration. We can use MDS to find back what the underlying map is. So when we put this as the input into MDS, this kind of distance matrix, MDS always works with a distance matrix, then we can obtain this visualization. So this is calculated by MDS on the basis of this distance table. And you will see, if you think of north-south a bit in this direction, that this is a pretty good representation of the different locations of these cities, right? So Berlin is to the east of London, and further east is Moscow. Beijing is much further to the east. Reykjavik is a bit more to the northwest, etc. So this is a fairly good reconstruction of the map based on this distance table. And this is always what MDS does. You insert a distance table that shows the distances between each of the observations. The observations here, in this case, are the cities. And you use the distance table to produce a two-dimensional or three or four-dimensional representation that preserves as much as possible the distances that are in this table. So the distance from this point Reykjavik to this point Beijing relative to Reykjavik to Oslo should be more or less what is here, Reykjavik to, where is it? Beijing here, and Reykjavik to Oslo here, right? So this is about 5 times larger, and in this plot it should also be about 5 times larger. Yeah, this distance should be 5 times this distance, because here this distance is about 5 times this distance. It can never preserve it exactly, but we approximate it as much as possible. Now, these distances are based on kilometers. We can certainly think of all kinds of other distances. We can think of a distance in just sort of the number of words that are different, or the number of, the percentage of words that is different, etc. We can think of different dissimilarity measures. So in this matrix, the number always shows how dissimilar are the two objects, or how far away from each other are the two objects. And then you get a visualization that tries to preserve as much as possible these distances. So in R, we first need to calculate the distance matrix. So there's the dist command, which takes a set of points. Depending on how many variables you get these points, and then it calculates a matrix that is the distances between each of the observations. And then we can use CMD scale, so this is classical multidimensional scaling, using this distance matrix, and it will produce the kind of plot that you just saw. There are other implementations of multidimensional scaling, in particular when the level of measurement is not a scale variable. So here we're talking about kilometers, that is a scale variable, but you could also have imagined some categorical variable, and then things become a bit more complicated. We won't go there now. Counts of words or counts of documents, as we are working with here, they are pretty similar to these distances, and so we can use classical MDS. Here's another example. So imagine you have a data set with a number of different countries and a range of different measures that all have something to do with economic development. Yeah, so we can think of the economic growth rate, life expectancy, infant mortality, fertility rates, or GDP. Right, so all these measures tell you something about economic development. And this provides a lot of information, and maybe we have more variables. But in this example, we have these 5 variables. And by having these 5 variables, it means we are working on a 5-dimensional space. We have 5 dimensions where the first dimension captures the increase, the growth rates, and the second axis or second dimension captures life expectancy, etc. And so we can place each country on the basis of the scores they have on each of those dimensions. And if we have even more variables, it becomes more complicated data to work with. And maybe we want to have 1 scale or maybe 2 scales to better position each country. We just want a scale from low to high economic development, and we're looking for this kind of underlying pattern. So imagine we've placed each of those countries in this 5-dimensional space. We've given them a position based on the scores on these variables. And we want to preserve the distances between them. So if Albania, in terms of the scores on these variables, is very different from Argentina, they should be far apart. Here you can see they're close here, they're close here, they're close-ish here, close here, but very different in GDP. Yeah? If we then take, for example, what is a good example? Benin. Benin versus Argentina is very different on almost all the variables. So Benin is much further from Albania than Argentina is from Albania in terms of these variables. And that means that if we want to use multidimensional scaling and we want to go to a 1 or 2 or 3-dimensional representation of this data instead of a 5-dimensional representation, we want to make sure that it does it in such a way that Benin stays further away from Albania than Argentina does, right? So that we preserve those distances. That is the key behind MDS. So if you do that with 2 dimensions on that data, you get this particular visualization. The command in R is given above. So we have this 25 countries scored in 5 dimensions here. We have scaled them because one problem that we have here is that the first column varies only a little bit, right? From minus 1.5 to plus 3 or so. The right column varies really a lot, yeah, from 100 to 20,000. If you would just calculate distances between observations, these distances would be much more important than these distances. And so the variables would not count equally. We would really just be looking at GDP per capita, sorry, because the numbers are just so much bigger. The variation in this variable is so much higher than the variation in this variable. So if you calculate the distance based on these raw numbers, the distance between 2 countries in terms of GDP is really the only thing you're evaluating. But we want to evaluate all variables. So what do? We scale them. We subtract the mean from every variable, we divide by the standard deviation of each variable, and the result is that every variable will have a mean of 0, a standard deviation of 1, so they will be all more or less in the same scope. So that is what the scale command does. Then we calculate distances between each of the observation, so we get the distance matrix. A matrix where every row and every column is a country, and the number in the cell is the distance between those based on those 5 scaled variables. Then we apply multidimensional scaling, and finally we produce a plot of this scaling. And this is what you get. So what was the example again that we looked at? We looked at Albania, Argentina, and Benin. And the argument was that Albania and Argentina should be closer to each other than Benin and Albania. Yeah? And so these distances are indeed preserved. Countries that are similar on those 5 measures, they end up together. Countries that are very different on those 2 dimensions, on those 5 dimensions, they end up far apart from each other. And we get sort of a mapping of economic development. Now, this is in 2 dimensions, so you can try to read it left to right or try to read it bottom to top, yeah? Or top to bottom. So on this left-right, on the left we have countries like Italy and the Netherlands and France and Greece and Croatia. They're all on the left. On the right we have Malawi, Benin, Pakistan, Cambodia, etc. Yeah? So this tells you this is 1 dimension, and this should be an important dimension of sort of underlying economic development. And then from south to north or north to south, here we have Romania, Croatia, and then China. Here we have Austria, United States, France. So you can try to think on what variables they differ most, but that is sort of a very different dimension from the east-west dimension. Yeah. So these are perhaps they are, for example, I think here you will find countries where maybe the GDP is a bit lower, but literacy rates or healthcare is high, etc. Yeah. Whereas here also these literacy rates, etc., are lower. So maybe they're in a different place for a different reason. You can try to go back to this data set and see what the main patterns are, but that I'll leave up to you. The bottom line is that we've used those 5 variables to come up with a 2-dimensional representation instead of a 5-dimensional representation. So we can visualize it and we can see which countries are similar in terms of economic development. So these countries are all similar in terms of economic development. Romania and Croatia are similar in terms of economic development. Netherlands, France, Australia are similar in economic development. And we can see where countries are positioned, which ones are very different from each other because they're in very different parts of the space, and which countries are very similar to each other. So in the next video, I'll talk about the next method, principal component analysis.